Welcome back. In the next lecture, in Fundamental of Electronics, we are going to discuss on active filters. In the previous two lectures, we have discussed in detail about operational amplifiers. How this operational amplifier is used for active filters. Let us discuss that. So, the introduction to active filters process signals by passing certain frequencies while rejecting the others. So, the frequency response of any op-amp circuit, what we have studied is important, and we will be choosing certain frequency region where we are interested in, while the other frequency region we will be rejecting it. And that has to be done with the help of filter. Active filters basically use op-amp, while the passive filters use RC circuits. So we should have a clear understanding of the operational amplifiers in detail. Then only we can understand about the active filters. Filters categorized by output voltage variation with input frequency. So we are basically sweeping the input frequency and then we are measuring the output voltage. So voltage is a function of frequency. Four basic categories of these active filters we will discuss. The first one is the low pass filter, high pass filter, band pass filter, and band stop filter. The advantages of these active filters over the passive filters are they provide a gain due to the active elements. High input impedance is obtained, low output impedance is the process, and the first filter that we are going to take is the low pass filter, and we will study the response. So as the name suggests low pass, so it will be passing the frequencies from DC to a certain critical frequency and attenuate the others. So the frequency which are selective here or the passes is from the DC level to the critical frequency level. The circuit of low pass will have a pass band in the frequency with minus 3 dB attenuation. We have studied the frequency response and introduced the concept of attenuation and the unit also what is dB in detail. If you have not seen those lectures, please go back and see the previous two lectures. The critical frequency is given by 1 by 2 pi RC for a single pole RC filter. So here you can see one network which is basically a low pass circuit having a source and the RC network, and the filter response is being shown with the magnitude response. So the magnitude response of the filter with respect to frequency is up to the critical frequency it will pass, and then it will fall with minus 20 decibel per decade. So the roll off frequency will be minus 20 decibel per decade per pole. So again, how many poles are there in the system? That also matter a lot. The bandwidth for the ideal case is equal to the critical frequency. So this is the bandwidth of the system which is equal to the critical frequency, and the system can have multiple poles, so it can fall with multiple roll off, that is minus 20 decibel, minus 40 and so on. High pass filter response, so it will be passing the frequency above the critical frequency and be attenuated below. So all the frequency below the critical frequency given by 1 by 2 pi RC will be attenuated, and this is the example of a single pole RC filter. So here in the network, we are having first the frequency will, with respect to frequency, the gain will increase and then become constant. So this is the frequency which will be passing. So it is above the critical frequency, FC, and all the frequency below it will be attenuated. Again, the rolling off will be minus 20 decibel per decade per pole. So here you have the minus 20 decibel per decade. And then if you have multiple poles, then again this will be multiplication factor of minus 40, minus 60 and so on. The practical limitations of these filters are op-amp's internal RC circuit limit the high frequency response. So basically we are having RC network. So what are the values of these RC which is the internal to the circuit? They will be limiting the high frequency response, means up to what frequency we can go in the pass band. Band pass filter, we are interested in passing the frequency between two critical frequencies, that is the lower critical frequency FC1 and the higher critical frequency FC2. So here we have the low critical frequency and this is the high critical frequency. So our bandwidth is basically the difference of the higher critical frequency minus the lower critical frequency. Whereas the center frequency is the geometric mean, that is the under root of Fc1 into Fc2. So this is what you have, the center frequency. We need to determine the quality factor. So quality factor is nothing but the resonant frequency or the center frequency by bandwidth. It is the reciprocal of the damping factor. We will discuss the damping factor in the coming discussion. So if the quality factor is greater than 10, we can say that that is a narrow band, and if the quality factor is less than 10, we can say that it is wide band. So determining the quality factor is important to understand the frequency response, whether Q value is greater than 10 or less than 10. When we discuss the band stop filter, it is basically rejecting the frequency between Fc1 and Fc2, that is the lower critical frequency and the higher critical frequency. So it will be rejecting and it will be passing the other frequencies. So the bandwidth will be Fc2 minus Fc1, and it is just the opposite of band pass filter. So band pass filter and band stop filter are just the opposite of each other. Now let us see the response of the filter and what are the characteristics. So we will be discussing three important characteristics. First one is the Butterworth, second is the Chebyshev, and the third one is the Bessel. So here you can see the comparative filter response. So you have the frequency on the x-axis and the gain on the y-axis. So if we take the Butterworth, so Butterworth is shown by the pink color. So it is flat, pass band, and you have minus 20 decibel per decade per pole and non-linear phase we have. So Butterworth is basically having a flat response up to the pass band. And then you have a decade of minus 20 decibel per decade per pole, that is the roll-off. And then you have a non-linear phase. Chebyshev filter response will have a steeper roll-off greater than minus 20 decibel per decade per pole, and it will have pass band ripples. So when we discuss the Chebyshev, it will be having a certain ripples you will be having in the response. Bessel on the other hand will have a linear phase and it will be minimal overshoot and suitable for pulse waveform. So wherever we need to take the pulse waveform, we can go with the Bessel because it is having the linear phase response. So we were talking about the damping factor, that the quality factor is the inverse of the damping factor. So what is this damping factor? Damping factor determines the response characteristic of these filters. They are given by, the damping factor is given by 2 minus R1 minus R2. So this is the circuit, which is a general active circuit, active filter circuit, where you have the op-amp and the op-amp is connected with the RC frequency selective circuit. We are giving the input voltage and measuring the output voltage. So output voltage is a function of frequency. Here you can see that voltage divider is connected in the form of negative feedback circuit, so which is given with to the inverting terminal of the op-amp. So here we can determine the damping factor as 2 minus the ratio of R1 and R2, which are forming the voltage divider network. So if you have a second order Butterworth filter, the damping factor will be 1.414 and the ratio of R1 by R2 will be 0.586. So damping factor is important because it decides again the quality factor of the circuit. Critical frequency, which decide the frequency response, the pass band and stop band of the first order RC filter, is basically given by 1 by 2 pi RC, and it is applies to both the low pass as well as high pass single pole configuration. Now if you have the more number of poles, you can basically have the greater roll-off rate. So here it is being given 1 pole, 2 pole and 3 pole, which is deciding the order of the circuit. Then you are basically having minus 20, minus 40, minus 60 decibel per decade as compared to the single pole, which is minus 20 decibel per decade. Now let us see the low pass filter with a single pole. So here you have the active circuit, which is a op-amp, and the RC selective frequency response circuit is connected. The input voltage is given, output voltage, and the feedback circuit is the voltage divider circuit, which is connected to the inverting terminal. So it uses one RC circuit and the rolling off will be minus 20 decibel per decade. So initially up to the critical frequency, if you see the frequency response, it will be linear or flat, and then it will be falling with minus 20 decibel per decade. So the critical frequency is 1 by 2 pi RC, and the gain, closed loop gain of the non-inverting case will be 1 plus R1 by R2 for the single pole low pass filter. Now, there is a term which is known as Sallen-Key in the filter configurations. So these are basically common second order configurations if you take, and these are voltage control voltage source. So Sallen-Key is important when we discuss about the two pole filter, and the rolling off will be minus 40 decibel per decade. So here again you can see this is the active circuit which is having a filter, the op amp, and the input we are basically connecting with a RC network, and the feedback we are giving with the voltage divider. So in this circuit, the critical frequency, because it is a two pole filter, will be having 1 by 2 pi and under root of combination of resistors and capacitors. So generally this resistor and capacitor are equal. So Ra equal to Rb and Ca equal to Cv. So we can say that the critical frequency is 1 by 2 pi Rc. Now the low pass filter can be cascaded. So multiple low pass filters can be connected together. For example, if you want to form a third order filter, low pass filter, then basically we require to form the cascaded two pole Sallen-Key filter plus one pole filter. So here you can see the third order configuration where we are basically having this as the two pole, and then you have the one pole. So totally you are basically getting the third order low pass filter. If you want to make higher order like a fourth order configuration, then in that case you can cascade two pole Sallen-Key filter. So here you have one Sallen-Key, another here you have one Sallen-Key. So you will be getting the fourth order, and the rolling off rate will be minus 80 decibel per decade. So cascading of filters we do when we want to get more number of poles in the filter response. Now let us discuss the high pass filter with a single pole. So you have basically a connection of RC network, which is selective frequency, to the op amp and the feedback circuit. You are having the rolling off rate as minus 20 decibel per decade up to the critical frequency, and then it is becoming flat. So critical frequency again same 1 by 2 pi RC, and this is limited because of the internal RC limit frequency response. But when you have to discuss the Sallen-Key, which is basically the two pole filter, then in that case you are having a circuit which is a combination of resistor and capacitor, because you need two pole high pass circuit. Then in that case R and C positions are swapped as compared to the low pass filter which we have discussed in the previously, and this response will be optimized by feedback resistors R1 and R2. So once we change these values of R1 and R2, the responses will be changed. So high pass filter is again reciprocal of low pass filter. The position of R and C we are changing so to get the new circuit. So if you need to cascade the band pass filter, so you can have the higher order circuit, whether we can have two second order or the third order network, then we can cascade the high pass and the low pass. So high pass and low pass, when we are cascading, we are basically getting the band pass, and this is a Sallen-Key filter. So here you can see that we are basically connecting one Sallen-Key, other Sallen-Key. These are basically two pole high pass and two pole low pass filter with a different critical frequency, FC1 and FC2, and then we can get the bandwidth of this band stop filter as a difference of FC2 minus FC1 with the center frequency as the root of FC1 and FC2. So these are suitable for wide bandwidth applications, the cascaded band pass filter. Now if you want to have the multiple feedback band pass filter, then in that case if you can see that the feedback whatever we are giving is multiple, then the center frequency can be changed. So center frequency can be changed depending upon the values of the resistors R2, C1, and we can put it in this formula. The gain will be equal to R2 by 2 times R1, and these resistors value we can find out with the help of the what quality factor we need for a particular circuit. So depending upon the applications of the band pass, we can form the multiple feedbacks and decide the values of the resistor to get a particular frequency band pass. State variable filter is one of the other type of filter which uses summing amplifier and two integrators. So here we are basically having a circuit of state variable filter, when we have a summing amplifier and then we have two integrator here, and the center frequency in this case again will be 1 by 2 pi RC, and the quality factor is given by 1 by 3 R5 by R6 plus 1. So this is the frequency response of state variable filter, whether you have the below the FC you have low pass and above the FC you have high pass. So this is the frequency which we have interested in band pass. So it provides a low pass, high pass and band pass output. So all type of responses we can get with the help of state variable filter. Bicquad filter is basically another type of filter which is having integrator, inverting amplifier, and again you have the integrator. So three combinations we can do it. That is known as the bicquad filter. So it will be providing the band pass and low pass output. So first we'll get the band pass and then we'll get the low pass. So here when we get the input voltage, the output of the integrator will be band pass, and then after the inverting amplifier and integrator we will get the low pass as the output. It will have a high quality factor, bandwidth independent of the center frequency. And when we require this band stop filter with multiple feedback, it is similar to the band pass which we have discussed earlier with modified resistor combinations. So these combinations, whatever we are using, if we change it, we can have the multiple feedback band stop filter. Band stop filter in the state variable form we can have by created by summing the low pass and high pass output. So here you can have low pass and high pass. These two are summed with the help of a state variable filter, and the input voltage is given, and the output that we get from the filter is basically the band stop filter. And so the common application of this one is basically when we need to have the 60 Hz noise rejection. The center frequency is set by the integrated RC circuits. So the center frequency whatever we need, if not, you will be setting up with the integrated RC network. We need to measure the filter response measurement. There are two different methods are available. One is known as the discrete point measurement. So let us discuss that first. So discrete point measurement, the circuit or the flowchart is shown where you have a sine wave generator and then there is a filter and you are measuring the input and output. So you set a constant input amplitude. So input amplitude you set it constant and then sweep the frequency in step from the lower frequency to higher frequency. Record the output at each frequency. So what is the output at each frequency, and then the plot the response curve. So this will be the plot and this would be the voltage gain, and you will be getting certain plot for different frequency range. But when the second method, which is the swept frequency measurement method, this is more efficient than the previous discrete method. Here we are using a sweep frequency generator and we are using the display the signal using a spectrum analyzer or the oscilloscope in XY mode. So here you have the spectrum analyzer which is displaying the output response. The sweep generator is sweeping the frequency. So this is sweeping the frequency and we can provide a continuous response curve using the sweep frequency response measurement. So the summary of this active filter discussion, we have covered the low pass, high pass, band pass and band stop filter. We discussed about the Butterworth, Chebyshev and Bessel characteristic responses. We analyzed the single pole, Sallen-Key, multiple feedback, state variable, bicquad filters, explained what is the concept of damping factor, critical frequency, the roll off rate, and we described the discrete point and sweep frequency type of measurement for the frequency response. So this complete our discussion on the active filters. Thank you for now. See you in the next lecture.